Hello, good evening. My name is Parth Joshi. I am currently a PhD student in the Department of Mechanical Engineering at IIT Bombay. I have been conducting these weekly problem solving sessions as a part of this NPTEL course on Introduction to Mechanical Vibrations. So, this is the seventh week. So, welcome to those who have joined this session. So, till now, we have looked at the concepts related to single degree of freedom systems, like damped and undamped vibrations, and free and forced vibrations. And we have also looked at two degree of freedom systems, like the free vibrations and forced vibrations of two degree of freedom systems. So in the in content for this week covers the concepts of tuned vibration absorbers, and the other concept is the critical speed of shafts. So these are the two main topics uh, for this week. So we would be covering some problems related to these topics. So before we proceed, so I would like to thank the NPTEL team for giving me this opportunity to conduct this online tutorial sessions. So uh, so before we can proceed with our session, so I see that someone has joined this meeting. So hi, so I can see the name as Luck TVT. So
Yes, sir. Good evening, sir.
hi. So what is your actual name?
DVT Vittal, sir.
Okay. So hi, welcome to this session. So uh, can you just briefly introduce yourself?
Yes, sir. Myself, Vittal. I have been attending this course since beginning.
Okay.
I have been working for BHL.
Yes,
Last
yes, right,
few
right.
classes also I have interacted with you. We are attending
Yes,
some troubleshooting issues at various turbines, compressors,
right, right,
BHL supplied equipment, sir.
right. Yes, yes. We
Yes,
had talked earlier. Sure,
yes, sir.
sir.
Yes, sir.
Yes, sir. So thanks for joining. Welcome to this tutorial session. So how was your experience with the tutorial sessions so which were done so far?
Very good, sir. Informative and useful for problem solving, especially.
Okay,
Without these inputs, we cannot proceed for problems
okay,
as they are very complex. No? So it is
right,
useful.
right. So did you find any of the content that has been covered, like first question is like, do you find it useful for the assignment problem solving?
Yes, sir.
You find
Definitely,
it.
sir.
Okay.
Mm.
And like, do you find it useful otherwise as well, like in terms of like the for your everyday day-to-day work? So has the content helped you in any way if in your day-to-day work?
Yes, sir. Uh, we are visiting few project sites where we got this vibration spectrum, some problems.
Okay,
So these are all useful, sir. This whatever this what we can say this literature, these fundamentals. So we can grasp something. We can answer to customers.
okay,
And
okay,
nowadays customers also very smart and they are learned. They have undergone some certifications also, like
okay,
level 2, level 3.
okay,
So that if you know some basics now, we can face them. We
right,
cannot give direct solution to them,
okay,
but at least we can interact. We can give some face to. We are the face of BHL. If
right,
you don't know anything now, they will criticize you.
right.
I either I saw. So
Mhm.
somewhat these fundamentals are very helpful.
Okay, 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 sir.
Definitely, We can
Yes.
tell what is the resonance, what is critical speed, what is frequency. At least
Right.
few terms we can learn, and we are doing this assignments also very useful.
Okay.
And
Okay.
Ashish Kumar sir also explaining uh, thoroughly on the
Yes.
board
Yes.
itself. He is
Yes. Yes.
solving so many equations.
Okay.
Is he simplifies such a way that very useful. And I am also attending that IIT Delhi sir. Uh, I forget his name. One
Okay.
professor. He also gives very good lectures.
Okay.
I am
NPTEL
fond of this.
course itself.
Yes, sir. NPTEL. That course is Elements of Mechanical Vibrations.
I see. Okay.
Uh, I can tell you name. I
Okay.
will recollect. So these two
Okay.
lectures I regularly listening.
Okay. Okay. Good. Good. Good to know. And thank you for sharing your experience and insights.
Yes,
So,
sir.
like, who are the typical customers with which you have been interacting? Like, which are the companies generally?
Mainly this Bharat Petroleum, Mumbai and Kochi refineries,
Okay.
as well as Bina and Numaligarh refineries. Similarly, other private and government means Indian Oil. Most of the refineries we are visiting: IOCL,
I see.
BPCL, HPCL, all petroleum industry and cement industry like Wonder
Okay.
Cement, Rajasthan, and similarly we have this Sri Cement Limited in Kodla also there, Jaipur also it is there, and we are
Okay.
visiting to Shamsel groups, Orissa Metallics, Shamsel, and
Okay.
Gallant Ispat, like it is in Gorakhpur.
Okay. Okay.
So many private customers are there, sir.
Okay. Okay.
ACC
Okay.
and this RCF, Rashtriya Chemicals Fertilizers, Nangal. Lot of around 100 customers we have,
Okay.
and we regularly visit this project site every month. 2 3 sites we visit, and not for only vibration problems, for complete erection and construction, commissioning, troubleshooting
Okay. Okay.
activities.
Okay. Okay. Great. Great. I think it's great to have you like to interact with you since you have such a wide experience in the industry. So thanks for joining. So
Yes, sir.
like you are providing like all kinds of engineering services or like some specific products to your customers?
Engineering services, sir. It is
Okay.
like when we are supplying the equipment from BHEL,
Okay.
it comprises rotary machine,
Okay.
piping, as well as static equipment. If it is
Okay.
STG, steam turbine and generator, we have turbine, gearbox, generator, and
Okay.
associated piping. And we have instrumentation, separate team is there, electrically separate team is there for that relay testing, generator panels.
Okay.
And we are from mechanical, so since the foundation verification, then installation of equipment, placing the equipment, then connection of that piping, welding, radiography, pipe centering, pipe parallelity, these all things it will include,
Okay. Okay.
and including hydro test, all NDT also. After that
Okay.
we have some centering and alignment, machine alignment, shaft alignment activities which causes vibrations also, no?
Right.
That
Right.
also we will verify. After that we will couple the machines, then we will, and commissioning stage will come. In
Right. Right.
between there is some pre-commissioning stage like audit, verifying so many systems whether it is in line with our design inputs, drawings or not. So oil flushing will be there through bearings, through pipelines. That oil will be flushed for many days, like 1 month, 2 months. Then steam blowing. For steam piping, there will be blown by a hot steam with high parameters.
Okay.
We will
Okay.
keep some certain criteria is there, keeping some target plates. We will evaluate how many dents or indentations are coming on that. This
Okay.
process
Okay.
also there in between, and we will
Okay.
check pipe parallelity and the equipment, turbine piping and the incoming piping, whatever the steam piping, whether they are aligned or not. Is there any misalignment in between them? If any
Okay.
offset is there, it will impinge forces onto the turbine. During running,
Right.
it will create unnecessary trouble. It will lifting of legs and vibration issue also it will cause.
Right. Right. Right.
Its centering will get disturbed, so it will cause clearances. One side closer or up and down will be closer, so it will cause directly on vibration part. This
Okay.
part we will do, and we will roll the machine. Roll means we are giving steam, and we are giving compressor like process gas, nitrogen, hydrogen, whatever the medium. and we will do reliability test for some hours, 24 hours, 72 hours as per the contract. These are all things we will do, sir. We will make some
Okay.
protocols, reports, and day to day we are giving constant inputs to the customers. Means this is very long process. It takes 2 years, sir, from foundation to complete commissioning and handovering of that project to the customer. This is technical services we are providing.
Okay.
This
Okay.
way we will complete the project. Post completion also, some material reconciliation, some things will be there. Troubleshooting. Suppose it got some issues like vibrations are coming, how to deal with them. Forwarding these inputs to our engineering departments are there. Corporate R&D is there, and in that as per that signature analysis, any it is due to unbalance, looseness. So our people will guide what to do, and our corporate team got such a equipment that inside to balancing also they will do. We are not doing,
Okay.
and we are only assisting them. They will come to the site, they will do balancing on generators, turbines. They will add some weights, removes weights. This process also there.
Okay. Okay.
So complete solutions we are giving from foundation to commissioning commissioning of the BHL equipment. For STGs means steam turbine and generator, which gives the power connected to grid. Second is steam turbine and compressor. Here steam turbine drives the compressor, so it is used for this like process and refineries, chemicals, fertilizers.
Right. Right. Right.
These two kind of equipment trains we are handling from Hyderabad.
Okay. Sure. Thank you. Thank you very much, sir, for sharing your
Yes, sir.
experience.
Yes,
So
sir.
I think the content for this week, I think, is very much related to your work in your industry. So I think this content will be useful for you for your work as well.
Yes, sir.
So, like before we proceed, so do you sir, have any specific questions for me like related to the content related to this week?
No, sir. Some assignment problems are pending,
Okay.
so that I can learn and I can solve those.
Okay. Sure. So I have selected some questions which I'm planning to solve in today's session.
Yes, sir.
So apart from that, like, have do you have any particular question?
No, sir.
Okay. Sure. I think then we can get started with the
Yes, sir.
problems. So these problems I have like selected so that they are similar to the kind of the problems that you would see in the assignments. So
Yes,
hopefully
sir.
that would be helpful for you. So, sir, are you able to see my screen?
Yes, sir. You can proceed.
Oh, okay. Sure. Thank you. So fine. So for our first problem is related to this vibration absorbers. So it is given that a machine runs at 3500 RPM. Its forcing frequency is very near to its natural frequency. So we will assume that its natural frequency is at related to this 3500 RPM. So now if we want to add a vibration absorber so that we want to reduce the amplitude of vibrations of the machine at this speed of operation. So what it is given at, if the nearest frequency of the machine is to be at least 15% from the forcing frequency, so we have to design a suitable vibration absorber for this system. So what it is given that, uh, so when we add a vibration absorber, the system will become a 2 degree of freedom system. Let us say if we model our basic machine as a single degree of freedom system, by adding the vibration absorber, we are adding one more degree of freedom to this system. So let us say if we model our machine like let us suppose like if we model our original machine as a lumped mass M1, which is uh, like the stiffness of the foundation between the machine and like the floor. Let us say that stiffness is K1, and let us say if we add a vibration absorber on top of that, let us say we call that it has a mass M2 and stiffness K2. So it has been given that the mass of the machine M1 is 40 kg, and the machine is running at 3500 rpm, so we are, and which is very close to its natural frequency. So let us say omega 1 is the natural frequency of this machine. So that is, we will assume that it is 3500 rpm, which is 3500 into 2 pi by 60 in terms of radians per second. So which is equal to 3500 into pi by 30, which is about 366.52 radians per second. Now, what will happen is that because of addition of this vibration absorber, our system is now it has become a 2 degree of freedom system. So to find out what will be the natural frequency of this machine, of this whole system along with the vibration absorber, we will have to solve for the equation of motion for this system. So let us proceed with that part. So to find out what will be the two natural frequencies, let us first uh, draw the free body diagram of these two this two masses M1 and M2. So let us say their displacement with respect to equilibrium position. Let us say we call them as x1 and x2 respectively with respect to their equilibrium positions. So let us draw the free body diagram for these two masses. So the mass M2 is subjected to a force K2 into x2 minus x1, and the mass M1 is subjected to a force K1 x1 vertically downward and another force upward because of the spring K2. And apart from that, we have a harmonic force, let us say F of t, acting on this mass, let us say F of t, which is basically the harmonic forcing, uh, which is causing the system to vibrate. So this force F of t, it can arise because of the eccentricity present in the machine itself. So that can, like, for example, if we have an eccentric mass in a rotating part, so that can be the harmonic force that is causing the unnecessary vibrations. So let us write down the equations of motion for this system. So since we have these displacements x, we will assume upward, vertically upwards, that's positive. So for the mass m1, there is a problem with my screen sharing. So the mass m1 is undergoing an acceleration, let us say x1 double dot is equal to the force F, and the spring force because of K2 is acting vertically upward. So we will call it as F of T plus K2 into x2 minus x1 minus K1 x1, and similarly for m2 it will be m2 x2 double dot is equal to minus K2 into x2 minus x1. So now if we want to rearrange this equation, so we can do it in this way. Like let us say m1 x1 double dot plus k1 plus k2 x1 minus k2 x2 is equal to f of t, and m2 x2 double dot plus, or rather minus, k2 x1 plus k2 x2 is equal to 0. Now we can rewrite this equation in matrix form. So this can be written in terms of mass matrix into the acceleration matrix, and then we will have a stiffness matrix. So the coefficient of x1 is k1 plus k2, and coefficient of x2 is minus k2. Similarly, coefficient of x1 is minus k2, and coefficient of x2 is plus k2. So this will be our stiffness matrix, and the right hand side we can write it as f of t comma and 0. So this is the uh, system of differential equations in matrix form. So now to solve for the natural frequencies, we will have to uh, find out the eigenvalues for the uh, matrix, which is when we substitute the solution of a certain form. So let us do that exercise. So for free vibrations, our uh, So for free vibrations at our natural frequency, so for that RHS should be equal to 0. So it should be actually a 0 0 matrix. So therefore let us substitute a solution of the form. So let us say x1 is some capital X1 e to the power j omega t, and x2 is some capital X2 e to the power j omega t. And let us substitute this into the differential equation. So what we will get is that x1 double dot is equal to minus omega square x1 e to the power j omega t, and x2 double dot is equal to minus omega square x2 e to the power j omega t. So now we can substitute this into the differential equation. We will get, so minus omega square m1 0 0 minus omega square m2 into x1 e to the power j omega t, and x2 e to the power j omega t, and k1 plus k2 minus k2 minus k2 k2 into x1 e to the power j omega t, and x2 e to the power j omega t is equal to 0 0. So now since e to the power j omega t will not be 0 for any real value of t, so we can simply eliminate that, and we can combine the terms on the left hand side and add the two matrices. So this is our resulting equation in terms of x1 x2 and omega square. So now for this to have a non-trivial solution, so trivial solution will be just x1 is equal to 0 and x2 is equal to 0. So that is not something that we are interested in. So we are interested in a non-trivial solution. So for that, uh, the determinant of this matrix, it should be uh, 0. So for that, so therefore we will write this determinant of uh, the matrix. So that determinant will be basically k1 plus k2 minus 1 omega square minus k2 minus k2 and k2 minus m2 omega square. So let us call this value as delta, and it should be 0 for having a non-trivial solution. So now let us solve for this equation delta is equal to 0. So for that we will simplify this further. So we will write down the value of this determinant first. So this is the expanded form of the determinant. So we can again rewrite and combine the terms. So this will be k1 k2 plus k2 square and this k2 square. So it will actually get cancelled. So it will be k1 k2 plus k2 square minus k2 square minus m1 k2 plus k1 plus k2 into m2 into omega square plus m1 m2 into omega to the power 4 is equal to 0. Now if we uh, divide both sides by m1 m2, we will get k1 k2 upon m1 m2 minus m1 k2 plus k1 plus k2 m2 upon m1 m2 into omega square plus omega to the power 4 is equal to 0. So let us write that k1 by m1, which is basically the natural frequency of this machine. Let us write it as omega 1 square, and the natural frequency of the vibration absorber, let us write it as omega 2 square. So we will get this equation in terms of this as omega 1 square into omega 2 square minus, so we will get here the first term will be k2 by m2, which is omega 2 square plus omega 1 square plus k2 by m1. So k2 by m1 we can write it down as k2 by m2 into m2 by m1. So dividing and multiplying by m2, and let us call this term m2 by m1 as mu. So we will get omega 1 square omega 2 square minus omega 2 square into 1 plus mu plus omega 1 square into omega square plus omega to the power 4 is 0. So we can again rearrange this equation and say, right, omega to the power 4 upon omega 1 square omega 2 square minus omega square into omega 2 square into 1 plus mu plus omega 1 square upon omega 1 square omega 2 square plus 1 is equal to 0. Now this is our characteristic equation, and the roots of this equation, so basically the roots omega square roots will be the our natural frequencies which we want to, for which we want to solve. So now we can, so basically we can see that the natural frequencies are a function of the ratio of omega 1 square and omega 2 square, and the ratio of the masses M1 and M2. So for the vibration absorber, we are selecting the stiffness and mass such that the natural frequency of this vibration absorber is nearly equal to the natural frequency of this machine. So omega 1 square is actually equal to omega 2 square in this case. So, so let us again simplify this equation further. So we will get omega raised to 4 upon omega 1 to the power 4 minus omega square into 2 plus mu in divided by omega 1 square plus 1 is equal to 0. So this is our characteristic equation. So now what we have been given, so we have been given that the uh, nearest frequency of the machine is to be at least 15% away from the forcing frequency. So our forcing frequency is same as our natural frequency. So omega 1 is omega 2 is this same as that natural frequency. So what we have been given is that omega by omega 1 is should be 85% or 0.85, which is basically 15% away. So before going to the original the natural frequency before reaching the natural frequency of the uh, machine, so it has to pass through the lower resonant frequency. So it basically our forcing frequency is now 15% away, so it is 0.85 of the actual natural frequency. So then so for this natural frequency to satisfy this, we will substitute this ratio of 0.85 in over here. So we will get 0.85 to the power 4 minus 0.85 square into 2 plus mu plus 1 is equal to 0. So using this equation, we can solve for the value of mu. So what we will get is 2 plus mu is 0.85 to the power 4 plus 1 upon 0.85 square. So from this we can get the value of mu. So we can solve this. 1 plus 0.85 to the power 4 upon 0.85 square. This value minus 2, so it will be basically 0.1065. So we got the value of mu, and so basically mu is m2 by m1, which is 0.1066, and we already know the value of m1, so it is given already as 40 kg. So now we can calculate m2, so it will be 4.263. So this will be our absorber mass. So we got the absorber mass m2, and now we have to find out the stiffness. So for that, we will again equate the natural frequencies. So k1 by m1 is equal to k2 by m2, which is basically omega 1 square is equal to omega 2 square. So which is now corresponding to the RPM of the machine. So which is 3500 RPM. Which we calculated as 366.52. So therefore K2 will be 366.52 into 4.263, which will be 1562.58. In newtons per meter. So this will be our stiffness value of K2.
Sir, small doubt.
Yes.
This for this 366.52, can we get square or it should be omega 1 square equal to 366?
Right.
Actually,
Sorry.
K,
Yeah, yes. It should be squared. Yeah, you're right. So this is actually wrong.
uh,
So
it will be in kilonewton meters.
yes. Right.
Mm.
Yes. Yeah. Thanks for pointing that out.
Sir. Actually, I got doubt. Okay, sir. Okay.
So in kilonewtons per meter, you will get around 572.7 kilonewtons per meter.
Yes, sir.
So this will be our stiffness of the absorber. So this is how we can design the vibration absorber given the design criterion of where the natural frequency of the 2 degree of freedom system should lie. So likewise, if we have this criterion that our natural frequency should be at least 15% away from the forcing frequency, we can design the vibration absorber accordingly. So any questions?
No, sir.
Okay. So then we can move on to our next problem. So it is given. So this is basically related to the whirling of shafts. So it is given that a shaft has an 80 diameter and 1.5 meter length. It carries a disc which has a mass eccentricity of 300 microns. So what we have to find out now that is the displacement of the shaft at a speed which is zero point 0.5 times of the its critical speed. So the equation for the displacement of the center of mass, it is given by, let us say, y is the displacement of the shaft. So and let us say that eccentricity of the shaft is e. So it is equal to, or in other words, we can write it as omega square by omega critical speed square minus 1. So it has been given that it is half of the critical speed. So this ratio of omega by omega critical, it will be 0.5. So this is given to be 300 microns. And this will be 0.5 square minus 1. So it will be 300 to 10 to the power minus 6 meter 1 minus 0.75. So I think I made a mistake actually in this formula. So it is should be, so it should be 1 minus omega n natural frequency by omega whole square. it will be should be 100 micrometer. Because we have been given that omega is omega n by this. So therefore we get that the eccentricity is 300 microns, but the displacement of the shaft is 100 microns only. So because the current speed of the shaft is half of the critical speed. So let us proceed to our next question. A cylinder shaft which is supported on two bearings at the ends, and it carries a disc which has an eccentricity E from the axis of rotation. The critical speed of the shaft is L, and let us say that the disc is replaced now by another one with the same weight, but it is mounted with an eccentricity 2E. So what will be the critical speed of the shaft in this second case? So the earlier critical speed is L, and now the displacement of the shaft is given by eccentricity E upon omega by N by omega whole square minus 1. So just now we saw that, and now we are saying that the disk will be replaced by another one. So the eccentricity will become 2E. What will be the effect on the critical speed of the shaft? So any guesses? So any idea, sir?
No idea, sir. Speed.
Okay. So basically we can see that from this equation we can see that there is no direct relation between what is the eccentricity and the critical speed of the shaft. So the
Yes, sir.
critical speed of the shaft is depending on the natural frequency of the shaft itself, not on the eccentricity of the disk. So the critical speed of the shaft in the second case will still remain the same because we are not changing the shaft in any way. We are only changing the disk. So by changing the disk with a higher eccentricity, the displacement of the shaft will change. So with higher eccentricity, there will be higher displacement. So it will be twice, but the natural frequency of the shaft is still same. So our critical speed will still remain the same. So the critical speed will be same as n.
Okay, sir.
So let us now look at this problem. A rotating machine with a mass of 200 kg is supported on a pedestal mount. It induces vibration into the surrounding area through its pedestal mount at an operating speed of 4000 rpm. A vibration absorber is added to reduce the vibration when mounted on the pedestal. The magnitude of the exciting force is 300 Newton, and the amplitude of motion of the vibration absorber like the auxiliary mass of it is limited to 2.5 mm. So we have to find out the what is the auxiliary mass and stiffness of the vibration absorber. So what we have been given is that the mass of the machine, let us say M1, is 200 kg. It is operating at a speed of 4000 rpm. So omega 1 is corresponding to this 4000 rpm. So let us say the harmonic exciting force is F naught and its magnitude is 300 Newton. And the amplitude of motion of the auxiliary mass, let us say X2, capital X2, is limited to 2.5 mm. So for to solve this problem, we have the basically two criteria to find out the uh, two criteria to find the stiffness and mass. So one is basically the criterion of amplitude. So one is basically amplitude of the mass. So we can represent this system in the same simplified form as the first question. So we can write this as a mass and stiffness M2 and K2 placed on top of this machine, which is again modeled as a lumped single degree of freedom system. So first criteria will be the amplitude of M2, so which is given as X2 is 2.5 mm. And we also know that this vibration absorber characteristic is K1 by M1 is omega 1 square, which is equal to K2 by M2, which is omega 2 square. So from these two criteria, we can find out what is the value of K2 and M2. Now to solve for the first criteria, we again need to go to the free body diagram and the differential equation. Now since we had already done that exercise earlier, so we can just directly reuse our same differential equation, because the system as such remains the same. So we can simply just reuse the equations of motion. So let us write down the equations of motion. So we again call the displacements as x1 and x2, and we also have a force F of t. So let us say this Ft, we can represent it as F naught sine omega t or something like that. this is our system of equations. So the solution will have two parts. One is the transient vibrations and other is the steady state forced vibration. So we are mainly interested in the steady state amplitude of the second mass M2. So therefore we will just be solve for the particular solution of this differential equation. To get the steady state amplitude. X2. So if the function f of t, let us say if we can write it in a complex number form, let us say we can write it as f naught e to the power j omega t. So for this kind of a particular solution, we can write down x1 in this form as capital X1 e to the power j omega t, and x2 is capital X2 e to the power j omega t. So here x1 and x2 represents the steady state amplitudes. So now if we substitute these in the differential equations, so we will get x1 double dot is minus omega square x1 e to the power j omega t, and x2 double dot similarly will be minus omega square x2 e to the power j omega t. So now if we substitute this in the differential equation, our matrix will become k1 plus k2 minus m1 omega square minus k2 minus k2 and k2 minus m2 omega square into capital X1 x2 e to the power j omega t and f naught 0 e to the power j omega t. So since e to the power j omega t is common and on both sides, so we can just ignore it, cancel it. So our equation will become k1 plus k2 minus m1 omega square minus k2 minus k2 and k2 minus m2 omega square x1 x2 f naught comma 0. So this will be our equation. So this is a linear equation in terms of x1 and x2, and we can solve it. So let us say we call this matrix as A. So let us say we call this matrix as A matrix. And this vector we call it as X, and this vector as F vector. So it is a linear equation of the form AX is equal to F. So X we can find out by as A inverse into F. So how do we calculate the matrix of A inverse? So we can simply apply Kramer's rule. So what we so for a 2 by 2 matrix, what we have to do for calculating inverse is swap the diagonal elements and reverse the sign of the non-diagonal elements and divide by the value of the determinant. So it will be 1 by delta into, so we can write down as x1 x2 vector will be 1 by delta into k2 minus m2 omega square k2 k2 and k1 plus k2 minus m1 omega square into f naught comma 0. So x1 we can write down as k2 minus m2 omega square into f naught upon this value of delta, which is k2 minus into omega square into k1 plus k2 minus k2 minus into omega square into k1 plus k2 minus m1 omega square minus k2 square. So we can observe that when the natural frequency omega square is same as the k2 by m2, which is the natural frequency of the uh, second mass, which is vibration absorber. So then that will be the amplitude of x1 will be reduced to 0. So basically the as expected x1, which is the amplitude of the machine, so that will be reduced to 0 when the frequency of excitation is the natural frequency of the machine. So that is the whole point of the vibration absorber. So let us derive the equation for the steady state amplitude x2, which we are actually interested in. So which will be k2 f naught upon k2 minus m2 omega square into k1 plus k2 minus m1 omega square minus k2 square. So if we divide the numerator and denominator by k2, so we will get f naught upon 1 minus, so m2 omega square by k2 into, and now if we further divide by the numerator and denominator by k1. So we will get, so this term, in this term k1 divided by k1 will become 1 plus k2 by k1 plus m1 omega square by k1 minus k2 by k1. So which will be f naught by k1 upon 1 minus omega square by omega 2 square into 1 plus k2 by k1 minus omega square by omega 1 square minus k2 by k1 . So when we substitute now for the vibration absorber, so omega will be omega 1, which will be omega 2 for the vibration absorber. So we want to see that when it is operating at the natural frequency, what is the steady state amplitude. So therefore we substitute this omega equal to omega 1 is equal to omega 2. So we get fc is equal to f naught by k1 . So this term will become 0. So 1 minus omega square by omega 2 square itself will become 0. And so therefore we will get minus k2 by k1. So our steady state amplitude, so our steady state amplitude is simply minus f naught upon k2. So we have been given that this is equal to 2.5 mm. So therefore we get, so since we have been given that this mass m1 omega 1 and f naught is 300 Newton and x2 is 2.5 mm. So we can calculate now that k2 is simply f naught upon x2, which is 300 by 2.5 mm, which is so which is 120 kilonewton per meter. And now we can find out m2 by using the criterion that m2 by, is equal to k2 omega square, is which is So 120 into 10 to the power 3 into 4000 RPM. So which is 4000 into 2 pi by 60 whole square. This is should be K2 by M2. So actually I made a mistake over here. So K2 by M2 is omega square. So M2 will be 120 into 10 to the power 3 upon 400 pi by 3 whole square, which will be which will be 0.6839 kg. So this will be the mass of the vibration absorber. So for the desired operating conditions. So this is how we used our two criteria that we had defined uh, for solving this problem. So any questions on this? Any questions on this?
No, sir. You can proceed.
No.
Okay. So then we can proceed to the next set of problems. So in this problem, it is given that there is an electric motor. So it is mounted over a cantilever beam, so which is fixed to the wall, and like on the free end, the electric motor is mounted. So it is given that the beam is observed to vibrate with large amplitudes at an operating speed of 1500 rpm of the motor. So it is proposed to add a vibration absorber to reduce the vibration of the beam. So since it is given that 1500 rpm is the uh, operating speed and the beam is vibrating with large amplitude, so it means that natural frequency of the motor is omega 1, which is 1500. So this total cantilever plus motor setup, it has a natural frequency of 1500 rpm. So we have to find out the ratio of the absorber mass to the mass of the motor, so that we have the lower natural frequency of this 2 degree of freedom system. So that should be 75% of the operating speed of the motor. So this is similar to our earlier questions that we had solved. So this criteria is similar to that. We have been also given that if the mass of the motor is 300 kg, we have to find out the stiffness and mass of the vibration absorber, and also find out the amplitude of the vibration of the absorber mass. So first of all, it is given that the electric motor has a rotating unbalance of magnitude of 2 kg centimeter. So the force, because of the harmonic force that it will cause, because of which the it will cause forced vibrations, it will be, let us say, small m is the eccentric mass and E is the eccentricity. It will be me omega square into sine omega t. So that will be our harmonic forcing. So let us say this is the force Ft, which will be acting on the electric motor. Now we can model this cantilever beam electric motor together as a spring mass system. So let us assume that this cantilever has some stiffness which can be represented as a spring with stiffness K1, and this electric motor, let us say we can represent it as mass M1, and the vibration absorber, it will have mass M2 and stiffness K2. So let us say we have the uh, displacements, we can represent them, let us say we assume that the displacements in downward direction are positive, and let us say we assume that this is the direction of the forcing. So whichever way we can assume it in either ways, so no problem with that. So this is similar to the two degree of freedom system that we have considered till now. So it has been given that omega is 1500 rpm, so which is 1500 into 2 pi by 60 radians per second. So omega is 1500 into pi by 30, which is same as 50 pi, which is, so omega is 157.08 radians per second. Now we can again similarly reuse the earlier equation of motion, because this is just still the same two degree of freedom system. So let us rewrite the equations of motion for this system. So this is the same differential equation that we got earlier, and we can still reuse that. And we had also derived the characteristic equation for solving for the natural frequencies of the system. So what we had done is that we had assumed solutions of the form x1 e to the power j omega t, x2 is capital X2 e to the power j omega t, and also assume like this RHS is equal to 0 for free vibrations. So then we got the matrix in this form minus omega square 1 plus k1 plus k2 minus k2 minus k2 and minus m2 capital omega square plus k2 into x1 x2 is equal to 0. So now to find out the roots of omega square, in terms of like omega square, we found out the determinant of this equation. So to get a non-trivial solution, so we, let us say we call this matrix as A. We basically said that determinant of this matrix A should be 0, and we got the characteristic equation in the earlier, as per the earlier questions, whatever we had solved. So we got the characteristic equation as k1 plus k2 minus m1 omega square into k2 minus m2 omega square minus k2 square. So this should be 0. So which is k1 k2 minus m1 k2 plus k1 plus k2 m2 into omega square plus m1 m2 omega to the power 4 is equal to 0. So we had simplified this equation earlier. So we had introduced this term mu, and also applied the conditions for the vibration absorber, that k1 by m1 is equal to k2 by m2, which is equal to this omega 1 square and omega 2 square terms. And finally we got this equation omega to the power 4 by omega 1 to the power 4, and all these terms. So let us rewrite this equation here. So now here this is the simplified characteristic equation that we get. So we have been given that our lower natural frequency, it should be equal to 75% of the operating speed of the motor. So this equation, let us say, will have two roots, which will be, let us say, omega 1 square and omega 2 square. So omega 1 square, let us say, it is the lower root. So then we have been given that omega 1 square by omega 1 square, it should be omega 1 by, or for that matter, omega 1 by capital omega 1 by small omega 1 is given as 75%, which is 0.75. So let us say this is our operating speed, which is given as 1500 rpm. So this is omega 1, which is corresponding to the 1500 rpm. So we will have two natural frequencies, omega 1 and omega 2. So this should be 0.75 omega 1. That's what we have been given. So now we will substitute this relation in this characteristic equation, because this is one of the roots, so it should satisfy this relation. So we will get 0.75 to the power 4 minus 2 plus mu into 0.75 whole square plus 1 is equal to 0. Or we get basically mu is 1 plus 0.75 to the power 4 upon 0.75 whole square minus 2, which is equal to 3 by 4 to the power 4 upon 3 by 4 whole square minus 2, which will be 4 to the power 4 plus 3 to the power 4 upon 3 square into 4 square minus 2. So we can calculate mu as 0.75 to the power 4 upon 0.75 whole square. So mu is 0.340278. So mu is basically mass m2 by m1. We already know what is the mass m1, so it is already given to us that the mass of the motor m1 is 300 kg. So m2 will be 300 mu, which will be 102.0833. So it will be around 102 kg. And now to find out the stiffness, we calculate the stiffness K2 by M2 is omega 2 square, which we had calculated according to 1500 rpm as 157.08 whole square. So K2 will be 102.0833 into 157.08 whole square. Whole square, which will be, so K2 will be
Two five one 8.81.
right.
Yes.
So something like this, around 251. So this will be the value of K2. Now, what the next question is to find out the amplitude of vibration of the absorber mass. So now how do we find that? So we had calculated x2 earlier. So for the vibration absorber, it is,
Force by stiffness.
sorry,
X2 it is force by stiffness. X2.
right, right. It was basically just F naught by K2. So our amplitude of the force F naught, it will be basically depending on the eccentric mass. So me into omega square. So that will be our mass, and our eccentric mass was given to be as 2 kg centimeters. So me omega square upon K2, and K2 itself is m2 into omega square. So it will be me omega square upon m2 into omega square. So it will be simply me upon capital M2. So it will be 2 into 10 to the power minus 2 upon M2, which was 102.0833.
And 000195 5 and 019 point triple 0195.
Right.
Yes.
So I'm getting 0.00196 meters. So it will be 0.196 meters, something like that. Millimeters.
Yes, mm.
Right. So this will be our steady state displacement of the vibration absorber. So this is how we can solve this problem. So any question?
No, sir.
Okay. So let us try to solve this question now. When an undamped vibration absorber having a mass of 30 kg and a stiffness K, so M2 is given as 30 kg, stiffness K2 is given as some K, it is added to a spring mass system of mass 40 kg and stiffness 0.1 meganewton per meter. So M1 is 40 kg and K1 is 0.1 meganewton per meter. The main mass x1, so let us say that x1 is 0 uh, when during its steady state operation under a harmonic force of amplitude 300 Newton. So F naught here is 300 Newton. We have to again find out the steady state amplitude of the absorber mass. So for that, for x2 we just did that same calculation, so it is simply F naught by K2. So for that we need to know K2. We already know F naught. So how to find K2? Any idea how to find K2?
This K by M equal to omega square.
Right. So we
K1 by
already know,
M1
right? We already know K1 by M1 is our omega square, which will be same
equal
as
to
K2 by M2.
K2 by
So since we already know K1, M1 and M2, we can just find out K2. So K2
K2
will be
equal to K1 by M1.
so 30 by 40 into 0.1 meganewton per meter. So it will be 0.075 meganewton per meter. So we can find out x2 as 300 divided by 0.075 into 10 to the power 6. So it will be 300 by 75 into 10 to the power minus 8, or oh, no, not
So it will be 10 to the power of minus 3, sir. This 75 by
sir,
1000.
right, sir. Yes. Yes, you're right. Yes, yes, sir. Yeah, sorry. So
4 into 10 power minus 3.
yeah, so basically x2 will be 4 into 10 to the power minus 3, which is 4 mm.
Meters, 4 mm.
4 mm. So that's the simply the steady state amplitude of this mass. So, so this is again a similar problem. We have been given that an air compressor of mass 200 kg, it has an unbalance which is given as 0.01 kg meter. So, so let us say this mass M1 is 200 kg and it has an unbalance of 0.01 kg meter. So it has an unbalance, so which will cause this force Ft. So Ft we can write it as me omega square sine omega t, and omega 1 is already given as 1200 rpm. So it is given that if the natural frequencies of the system are at least to be 20% away from the impressed frequency. So this is our omega 1. So for it to be 20% away, so let us say omega 1 and omega 2 will be our two natural frequencies. So with our absorber, so our system will become like this. It will be like the same way as our earlier representations. So so we have to find that. So this should be 20%. So so therefore we can write that omega 1 is zero point 0.8 or 80% of this omega 1. So we have to find out the M2 and K2. So for that we again go back to our same characteristic equation. So because this system can be still represented in the same way as our 2 degree of freedom system, our characteristic equation that we had derived, which is omega to the power 4 by omega 1 to the power 4 minus 2 plus mu omega square by omega 1 whole square plus 1 is equal to 0, where mu is this ratio m2 by m1. So here we have to basically find out mu, and we have been given that this ratio of omega 1 by omega 1 is 0.8. So by substituting this into the characteristic equation, we will get 0.8 to the power 4 minus 0.8 whole square into 2 plus mu plus 1 is equal to 0, or mu we can write it as 1 plus zero point 0.8 to the power 4 upon zero point 0.8 whole square minus 2. So can calculate mu as 1 plus zero point 0.8 to the power 4 upon zero point 0.8 whole square 0.2025. So M2 will be mu M1, which is 200 into 40.5 kg. So the next step is to solve for the stiffness. So we have been given the natural frequency. So we have been given that this natural frequency K1 by M1 is omega 1 square is K2 by M2, which is omega 2 square. So this natural frequency is 1200 rpm. So omega 1 is 1200 rpm, which is 125.6637 radians per second. So K2 will be M2 omega 2 square, which will be
639,512.64.
right.
Okay.
Yes, you're right. So nearly 639.5 mega Newton per
Kilonewton.
meter, kilonewton per meter.
So kilonewton per meter.
Right, right, right. So that is how we can solve these kind of problems. So basically we use these criteria of, first of all, the natural frequency uh, of the original machine, and we basically design the vibration absorber based on the criterion of where should the natural frequency of the 2 degree of freedom system should lie, based on the uh, original that as a fraction of the original natural frequency. So this is how we can solve these kind of problems. So I think we can conclude this session for today. So this is that's all for today from my side. So any questions, sir, which you have?
No, sir, lecture is very good, very helpful for solving the toughest problems in the assignment. And sir is also teaching very nicely. And I was telling, na, sir, I was also enrolled for another course from IIT Delhi.
Yes, 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 yes.
The professor was Ashish K. Darpe or
Okay,
Darpe.
okay, okay, okay,
But that was also little bit difficult. This
okay.
itself difficult. So I could not continue that course. At least I
Oh,
am trying to this time complete this course.
okay,
Next year I will complete the elements of vibration.
Okay, okay,
That's are also very exhaustively explaining. No issue,
okay.
but it is somewhat more difficult.
I see.
It-
Okay, okay,
Uh, this itself is difficult. We are struggling to pass this exam this time at least.
okay, okay.
On 24th exam is there.
Yeah,
We will try. If I am in Hyderabad, I will attempt the exams.
okay.
Mm.
Sure, sir.
Last time I cleared missionary diagnosis from IIT Kharagpur.
Okay,
I
okay,
forgot his name, that professor name.
okay.
IITnoise.com is there, na? That professor taught.
Oh, okay, okay,
It was also very helpful, sir.
okay,
I hope
okay.
this time I can finish this course.
Yeah, I think definitely. Yeah, sure, sure.
And I have one doubt, sir. This moment of inertia we are calculating na, for circular objects.
Mm-hmm.
Our professor is teaching it is 5D power 4 by 64.
Right.
Some lecturers it is teaching 5D power 4 by 32.
So it depends on
Somewhat.
which axis you are taking about. So like,
Okay.
let me just show you over here itself. So if
Mm,
you have a like a cylinder, and let us say you have some x, y, z axis. Let us say x, y, and z. So your moment of inertia, let us say j about z, and if this diameter is, let us say, t, so it will be pi d to the power 4 by 32. If you take the
okay.
moment of inertia about this z axis, and if you take the moment of inertia about the x axis or y axis, it will be, anyway, it will be the same because it is symmetric. It will be pi d raised to power 4 by 64.
60. Okay. Okay.
So it depends on the axis which about which we are taking. So for torsion problems, we will be generally referring to this jz, whereas in case of bending,
Yes, sir.
we would be referring to this jx or jy.
Yes, yes. I understood, sir. Okay.
Right.
Mm.
Sure. So thank you, sir.
Generally, for cantilever problem, they have used this 5D for 4 by 64 because it is bending. Okay, sir.
Right.
Thank
Right.
you for clearing it out.
Yeah. Yeah. Sure. Thanks. Thanks, sir, for joining. So I think we can conclude today's session over here. Um,
Yes,
we
sir.
can.
Thank you very much, sir.
Yeah. Thank you. Thanks for joining, and thanks for sharing your experience. So hopefully we'll meet in the next week, um, in the next problem solving session. Thanks
Yes,
for
sir.
attending, sir.
Thank you. Thank you, sir.